Good day, everyone. My name is Marie Wesley Andado. We are the Group 4. Me and my group mates will going to report about the detection limits. Before we proceed to our introduction, I'm going to read our objectives for this lesson. Objectives: discuss the detection limits, discuss the sensitivity and detection limits, discuss and explain the sample problem of detection limits. This is our table of contents. Introduction. An analytical method's detection limit specifies how low a concentration can be said to be measured. Low ones are preferred by users, laboratories, and equipment manufacturers. Honesty is required in industries that are subject to environmental control. Environmental laws, on the other hand, usually pertain to more complicated detection tests, assays, or surveys, as opposed to the simple measurement operation that gave origin to the detection limit idea in analytical chemistry.
What is detection limits? Did you know the detection limit DL is the lowest concentration that can be reported with a high degree of certainty. There is a detection limit for every analytical technique. Equation defines the detection limit in a practical sense for methods that require a calibration curve. In additional information, it is the analyte concentration that produces a response equal to confidence factor times the standard deviation over the calibration sensitivity.
Detection limit. Based on visual approach, detection limit is determined by the analysis of sample with known concentration of analyte and by establishing the minimum level at which the analyte can reliably detect it. The detection limit is obtained by analyzing a sample with known analyte concentration and determining the lowest level at which the analyte can be consistently identified.
The next is sensitivity and detection limit. Sensitivity is often used in describing an analytical method. Sensitivity, most often used as the calibration sensitivity or the change in the response signal per unit change in analyte concentration. The calibration sensitivity is thus the slope of the calibration curve. If the calibration curve is linear, the sensitivity is constant and independent of concentration. If nonlinear, sensitivity changes with concentration and is not a single value. The calibration sensitivity, it does not indicate what concentration differences can be detected. The noise in the response signals must be taken into account in order to be quantitative about what differences can be detected. The next is, in this figure, you can see the calibration curve of response for the R versus concentration or the C. The slope of the calibration sensitivity or the M. And the detection limit or the DL, it designates the lowest concentration that can be measured at a specified confidence level. While the analytical sensitivity, it is the ratio of the calibration curve slope to the standard deviation of the analytical signal at a given analyte concentration. The analytical sensitivity is usually a strong function of concentration. The next is the detection limit. So the detection limit or the DL is the smallest concentration that can be reported with a certain level of confidence. Every analytical technique has a detection limit. For methods that require a calibration curve, the detection limit is defined in a practical sense by equation 8 to 22 It is the analyte concentration that produces a response equal to K times the standard deviation of the blank SP. In this picture, the DL or the detection limit is equal to K, where K is called the confidence factor, over M, where M is the calibration sensitivity. The factor K is usually chosen to be 2 or 3. A K value of 2 corresponds to a confidence level of 92.1%, while a K value of 3 corresponds to a 98.3% confidence level. So the detection limit, it is reported by researcher or instrument companies and is not applied to real samples. The values reported are usually measured on ideal standards with optimized instruments. The next is the linear dynamic range. The linear dynamic range of an analytical method most often refers to the concentration range over which the analyte can be determined using a linear calibration curve. As you can see in the lower limit of the dynamic range, it is generally considered to be the detection limit, while in the upper end, it is usually taken as the concentration at which the analytical signal or the slope of the calibration curve deviates by a specified amount. The next is the linear calibration curve. So it is referred because of its mathematical simplicity and because it makes it easy to detect an abnormal response. So this is the example of the linear calibration curve. The next is the nonlinear calibration curve are often useful, but more standards are required to establish the calibration function than with linear cases. So this is the example of the nonlinear calibration curve. So the next is the large linear dynamic range. So it is desirable because a wide range of concentration can be determined without dilution of samples, which is time-consuming and a potential source of error. So this is the example of the large linear dynamic range.
Quality assurance of analytical results. Analytical methods are applied to real-world problems. The quality of results as well as the performance quality of the tools instruments used must be evaluated constantly. The major activity involves are quality control, validation of results, and reporting. So the quality assurance of analytical results is the process of detecting the analytical errors within the lab to ensure both reliability and accuracy of test results. Control charts. A control chart is a sequential plot of some quality characteristics that is important in quality assurance. The chart also shows the statistical limits of variation that are permissible for the characteristic being measured. So there are two types of control limits, the upper control limits and the lower control limits. A control chart always has a central line for the average and upper line for the upper control limit and the lower line for the lower control limit. These lines are determined from historical data by comparing current data to these lines, and you can draw conclusions about whether the process variation is consistent or in control in unpredictable. Next po. Statistical control is a condition describing a process from which all special causes of variation have been removed and only common causes of variation remain. On a control chart, processes that are in statistical control show no subgroups outside the control limits, no runs, and no non-random patterns. So the use of statistical control is to remove the influence of a particular factor that could not be eliminated or controlled by the experimental design in order to better analyze.
Good day, everyone. My name is Marie Wesley Andado, and I will explain to you the sample problem we have. Chromatographic measurements determining LOD and the LOQ based on the calibration curve. International Committee on Harmonization, or ICH, lists 3 ways to determine the limit of detection, LOD, or limit of quantification, based on evaluation, based on signal to noise, based on the standard deviation of the response and the slope. The ICH indicates that LOD, which they call DL, the detection limit, can be calculated as LOD 3.3 lowercase sigma over slope, and the limit of quantification, which they call QL, the quantitation limit, LOQ equals 10 lowercase sigma over slope. So here, lowercase sigma is the standard deviation of the response, and S is the slope of the calibration curve. S is estimated from the slope of the calibration curve for the analyte. Uppercase sigma can be determined in one of 2 ways based on the standard deviation of the blank, where blank samples are run and the standard deviation is determined. This is equivalent to the standard deviation of the noise. So in this figure, I've listed a set of concentrations, nanograms per milliliters, and signal area for a calibration curve. This data can be analyzed by a linear regression algorithm, such as is included in most data system software. I've chosen to use the linear regression data that can be obtained in Microsoft Excel. On the upper right, I have listed some of the key data presented in the regression report. The 4th item down, the standard error, is the standard deviation about the regression line for the interdata set, which I am using as lowercase sigma for the ICH technique. The slope of the calibration curve is listed at the bottom, labeled as the concentration coefficient. Using this number, we can calculate LOD equals 3.3 times 0.4328 divide into 1.9303 equals 0.74 nanograms per milliliters. In a similar manner, LOQ equals 10 rather times 0.4328 divide into 1.9303 equals 2.2 nanograms per milliliters. I would probably round this up to 1 nanograms per milliliters, and 2.5 minus 3.0 nanograms per milliliters. So the values calculated above should be considered estimates of the LOD and LOQ, and must be demonstrated by injecting multiple samples. For example, N is equals to 6 at the LOD and LOQ concentrations. If the results meet performance requirements, the LOD and LOQ have then been shown to be correct. Here is where the other LOD and LOQ techniques can be useful. Do the proposed LOD and LOQ appear to be visually reasonable? Thus, the LOD consistently meet the SN of 2H requirements of 3 to 1 or 2 to 1. Thus, the LOQ consistently meet at SN or 2H of 10 to 1 and have acceptable precision. Example, 15%. So I find that the determination of LOD and LOQ based on the calibration curve to be much more satisfying from a scientific standpoint. The visual and SN techniques seem too arbitrary to be anything other than confirming that the regression technique gives reasonable values. Remember, however, no matter which techniques you choose, the ICH requires that as part of the validation process, you should analyze a suitable number of samples, prepared at or near the LOD and LOQ to demonstrate that the proposed method limits are appropriate.
Sample problem number 2. Determining concentration detection limit or LOD and limit of quantitation or LOQ with the same problem. The problem goes like this. Given a slope of 1.54 times 10 to the third absorbance unit per molarity, find the limit of detection and limit of quantitation. To find the detection limit and limit of quantitation, the LOD is equal to 3S over M and LOQ is equal to 10S over M, where S is the standard deviation and M is the slope of the calibration curve. Given a slope of 1.54 times 10 to the third absorbance unit per molarity, the LOD is 3S over M, or 3 times 0.0010 absorbance unit divided by the slope 1.54 times 10 to the third absorbance unit per molarity, which is equal to 1.9 times 10 to the negative 6 molarity. This or 10 times 0.0010 absorbance unit divided by the slope 1.54 times 10 to the third absorbance unit per molarity, which is equal to 6.4 times 10 to the negative 6 molarity. This rounds to 6 times 10 to the negative 6 molarity. Since standard deviation will always be recorded to one significant figure, the limit of detection and the limit of quantitation that follows should always be rounded to one significant figures. So we come up with an answer. LOD is 2 times 10 to the negative 6 molarity and LOQ is 6 times 10 to the negative 6 molarity.
That's all for our report. Thank you for listening.